In this video, we're going to consider simple linear regression, and we're going to consider it in two different ways. First, we're going to consider it as a general linear model, and secondly, we're going to consider it as a generalized linear model. And the reason for doing this is twofold. First of all, it's going to reinforce the concept of a generalized linear model. And secondly, when we do Bayesian analysis, we'll be doing simple linear regression as a generalized linear model rather than the general linear model, which is what you're probably more familiar with. It's worth noting, however, that both of these are going to give exactly the same answer. So let's begin with simple linear regression as a general linear model. So, what we have is our dependent variable is going to be equal to this. We've got an intercept, a slope, the independent variable, and a residual. And this is going to be a two-stage process. In the first step, we're going to say mu I is equal to alpha plus bxi, and it's worth noting that mu I is going to be determined deterministically. There's not going to be any variable. So if you had two different individuals with the same particular value of x, they would have the same particular value of mu. However, when you actually obtained a value for them, they might have different values because of the residual, but they would still have the same value of mu I. And we can think of mu I as being the expected value of yi. So that's the first step. We get mu I, and then to get our yi, we start off with mu I, and then we add on to it a residual, and the residual is deemed to arrive from a normal distribution with a mean 0 and some sort of standard deviation, sigma, that we're going to have to specify. So from this distribution, we draw the residual, we tack that onto the expected value, and that'll give us our observed value. So that's the general linear model. Now let's think about the generalized linear model. Again, a two-step process, and the first step is going to be the same. We're going to say that mu I is equal to alpha plus bxi. The difference comes in the second step. How do we get our value of yi? What we're going to assume is we're going to have a normal distribution. It's going to have as its mean a value of mu I. We're going to have to specify a standard deviation, and then yi will occur as a random draw from this distribution with a mean of mu I. So again, we see the distinction between these two approaches. With the general linear model, we start off with mu I and tack on a residual. In the case of the general linearized model, we start off with mu I. We make that the parameter, the mean parameter of our normal distribution, and then we randomly draw an observation from it. So to further think about this idea of a generalized linear model, let's think of the components of a generalized linear model and compare them for logistic and simple linear regression. So if we think about the first component, which is the link function. So when we went over logistic regression, the link function was the ln of p over 1 minus p, And to get what we're really interested in, which is P, we got to say that P was equal to E fx over 1 plus E the fx. For simple linear regression, we're going to start off with mu, and we've already got what we want. So if we think about what we did with logistic regression, we refer to this as a logit link, because this was the logit. Here, we refer to this as the identity link. And the word identity makes sense because what we've got on this side is identical to what we've got on that side. The second component of a generalized linear model is the linear function. In the case of logistic regression, in the case of simple linear regression, it's the same. It's alpha plus bxi that determines the link function deterministically. So in the case of logistic regression, it would give us the link function. In the case of simple linear regression, it gives us the identity function. And the third component is the distribution. So in the case of logistic regression, we had a Bernoulli distribution. We had the value of P, it'd be P right there, 1 minus P right there. Got that from there. And then we would randomly draw one value to get yi. In the case of simple linear regression, we've got a different distribution, not a Bernoulli distribution, but rather a normal distribution with some value mu I that we need to specify. It's determined by our linear function. Some value of sigma that we need to specify, and then the observed value is a random draw from that distribution.